district heating is a key solution for the energy transition, and it's really answer all your needs when it comes to replacing thermal systems. So it's a solution that cuts CO2, reduce the cost, increase energy security, and is a technology ready to be adopted. When we speak of district heating, anyway, we are not speaking of only one technology. We're speaking of something that started, almost 2,000 years ago, with the Romans using it to warm up their bath. But if we look only at the last maybe 10, 15 years, for the sake of this webinar, we see three main technology and evolution of the technology. So third generation district heating, that is the networks that we are using today. Fourth generation of district heating, that are the network that we are building. And fifth generation, so the last one, the one that we are designing and planning today, and will be operational in few years. So this is a bit, let's say, the vocabulary that we will be using today, and this is a bit also the technologies that we are working on in Planeto. Few more words on each of them for the one that are not super familiar with all these solutions. So third generation district heating, it means a supply temperature that is quite high, can go up to 100 degrees, is connected to existing building. It's something that is already existing, is super widespread in Europe. We have more than 200,000 kilometers of pipes of third generation district heating in our cities. Is a cost-effective solution, and is a solution that starts to use digital tools for the optimization. These kind of are historically, let's say, more monodirectional. So we have a heat source generating heat that is distributed directly to the existing building. Then we have fourth generation of district heating, so lower supply temperature between 40 and 70 degrees, connected with buildings that have less energy consumption. Here we are starting to look at system integration, so it's not anymore just one heat source producing and delivering to buildings, but we have different sources, and we start to see the integration of renewable. So we have biomass, we have heat pump, we have waste incineration, and it starts to be more complex networks. Finally, we move to the fifth generation of district heating and cooling, because this is the big revolution of this kind of network, integration of cooling. These are also called Anergy networks, because exactly have with very low temperature. And this is a bit the focus of today, also what Jonathan will show you later. These networks are really now the top of this technology, because they allow to integrate renewable, so local renewable resources. We can use heat wave, seasonal storage, geothermal, is very decentralized, so it allows to really scale at city level, and can offer at the same time heating and cooling. That's something that basically everywhere in Europe, also here in Switzerland, we are building network with these needs, because exactly cooling needs are growing. With the evolution of the technology, we had also an evolution of the complexity of designing and building district heating. So while before was relatively easy for me, most of you are working on the topic, so they know that it's not easy at all, but was a bit easier to bring, let's say, the heating from one place to the other. Today, instead, we look at this new network, we have to work with the building demand simulation, so to understand how the energy demand is changing over the next 50 years of the life of this network. We need to integrate climate change, we need to integrate building renovation, so that's a big topic. Then we have the source identification. So historically, district heating was, we know there is some heat, maybe industrial, we want to bring it somewhere else. Now we are doing active work in looking for sources of renewable energy, also at local level, that can be integrated into systems. So that's something that requires a different kind of expertise. Then the design of the system. The system are more complex. There are multiple loops, different pressure, different temperature. I mean, all of you know the different valves that have to connect primary circuit, secondary circuit. So that's quite challenging from the tech point of view. Finally, to the simulation, so how all these systems together are actually integrating, how they are working together to really have the optimal work of these systems. And finally, here is the last of our point, but probably it comes always at the beginning of the planning, is the economic assessment. So to understand very early what are the business model that are that make sense for that projects, what is valuable or not, and all the indicators such as the return of investment, the cost of the megawatt hour, all things that are very important when designing projects that are becoming not only a technical solution, but most of the time become a proper investment for the operators and for the utility. So all this complexity, we tried actually to solve all this complexity with our software Tessa, the Thermal Energy System Simulation Assistant. As Julia was saying before, this software is the result of many years of work in the university on the research on the topic that we just mentioned. So thermal network, energy model, climate science, data visualization, and GIS. And so many years of research on this topic, and the last basically 2 since we created the company, of working with our clients with real life projects to really bring all this science to the market, to the users, to give them a tool that allows them to start to cover all the phases of the design, so from the feasibility all the way to the construction, but also to tackle the daily problem that we have when doing district heating, so pipe sizing, geothermal probes, thermal storage, so all the more, let's say, daily annoying also problem of district heating. On this part, I will leave the word to Jonathan to really go through the software to show you our solution. And we are here. See you at the end of our webinar. Thank you very much.
Thank you. I'll stop sharing now. Stop screen sharing. So now you should all see Jonathan's presentation. The floor is yours. Jonathan, you're still muted.
Okay.
So I hope you hear me okay?
Yep.
Yes. So yes, exactly. We developed Tessa to address each of these points, each of these pain points in district heating projects. And in particular, what we want to talk about today is how we focus on the future. So how we can solve all of these points, of course, simulating demand, designing systems, doing economic assessment, in the context of really 2 key things. One, which is the need to use renewable energy, as Stefano was saying, and the second, which is to address cooling energy demand, which we see as growing quickly in Europe and actually around the world. And indeed, in some places, cooling demand is already the main heat energy, the main thermal energy need, basically the main thermal energy service need, shall we say, in the built environment. And so how we approach this in Tessa? Well, firstly, we have to, of course, analyze the heating and cooling demand. This is something we built into our software from the beginning. What we are able to do is we have a data-driven model of the Swiss buildings, so we can simulate how they behave both today and how they will behave in the future. So, for example, here you have some example energy demand curves for today for this little village. Actually, this picture's in Satigny, so it's not far from where we are right here. And we can visualize this is what the aggregate energy demand looks like today. And in the future, in 2040, we can see a huge increase in cooling power demand. So that's driven by rising temperatures, rising requirements to cool spaces, and changes to the buildings themselves. And so this is really the first step to see, well, the kind of solutions we need to be planning and building now are not the kind of solutions that we've been designing in the past, burning fossil fuels to get 100 degrees, because we have to address these needs which are changing. Then, of course, we have to connect all the buildings together. that means laying out pipework, dimensioning pipework, and in particular, what we're looking at more and more is the combination with shallow geothermal. So shallow geothermal is where then you design, you develop a borehole field. So you drill maybe a couple of 100 meters depth, generally considered between 100 and 400 meters. The advantage with a shallow geothermal, of course, is that apart from being a relative, quite readily available renewable energy source, because many places you have the ground conditions that you can build it, if of course you have the space, but you can also use it for cooling as well. So with our tool, what we're able to do is design a network layout, but also dimension then the geothermal borehole field that can feed this network, and dimension, of course, all the pipes that are needed, calculate pressures, for example, critical pressure paths. So really from everything you need from basically zero until having a network. And I'll enter this in a bit more detail in the examples and case studies. And of course, as we said, I mean, maybe we should put this up front, because that tends to be at the forefront of people's minds when people are actually doing this, which is the scenarios, the KPIs, particularly financial KPIs. These are all things which are automatically generated or come out as a function of your design. So you really can very, very quickly generate different scenarios. So we have automated tools for design the networks, do of course the demands. You can input costs. We also provide default costs, and that allows you to create sort of report pages like you see here, where you can straight away see investment, lifespan, levelized cost of energy, everything you need to really decide whether a project should go ahead, or if we have to adapt somehow the design in order to meet these needs. So now I wanted to go through a few of our, one particular real-world case study, but a quick overview of some of our interesting applications so far. We've done now quite a few projects, and here are a few highlights of, just to show that we're working, of course, on the top row in our home zone of Switzerland, shall we say, in Grand Vaud. That we did a design that I will present now in a bit more detail. We've worked with partners also in Schaffhausen, more for just energy network routing. And Otson, we worked there with our partners at GeoImpact with the more the part of strategic energy planning, so understanding really the clusters of buildings where you could put district heating. Right now, we're working also in Geneva Canton to look at 5G DHC studies, so fifth generation networks that are going to use geothermal, and I will also show you some examples of this. And just a bit more exotic, we're also looking now at case studies in Turkey, funded actually by IFC World Bank. So it's also a topic also of investment and development around the world, and not only in Switzerland today. And likewise, we also start to have some activities in the UK, Scotland, where there is, I don't know, some of you may be aware, an impulse in the UK to expand district heating systems with a new policy. So to look at the first case study, it's in Grand Vaud, this very nice village up on the slopes beyond Lausanne. So the challenge here, of course, is Grand Vaud is a UNESCO World Heritage Site. The whole area is very much protected, but with our partner Strom, we were helping them to design a entirely fossil fuel free heating system that could replace the current oil burning system they have in. And we think this is a very nice example because, of course, UNESCO is about protecting heritage, and that heritage should really be protected sustainably, because we want to preserve the past for the future and not ideally be doing that in an unsustainable way. Given the constraints of the site, of course, very, very tightly packed buildings, relatively protected agricultural land, it was firstly not really possible to put classic heat pumps on every building. This is because of the historic protections, the architectural protections. while individual solutions, by putting, for example, a geothermal borehole for each building, would consume too much space. And so this was the basis of a pilot project led by Strom and supported by the Swiss Federal Office of Energy. The solution was to create, or at least to propose the creation of a network underneath the streets. The streets are planned to be open anyway because all of the pipe working will have to be redone, and to do a 5th generation network using geothermal probes distributed underneath the streets of the village. For this meant being able to use exactly all of the tools that we have developed in our software, so projecting the heating and cooling demand over the next 50 years, using this to optimize the geothermal field by regenerating. So one important thing with shallow geothermal is, of course, you drill to relatively shallow depths, you reach moderate temperatures, less than 20 degrees, you extract energy from the ground, but in extracting the energy from the ground, the heat, you cool it down. So either you have to limit the amount of extraction that you do so that the ground stays warm, so it reheats naturally, or you have to regenerate by re-injecting hot water, usually in summer, and usually by using water that's been heated up by cooling a building. When you can do this, and what our software is able to do is optimize this so that we can calculate the reduced number of geothermal boreholes that you need, since you know that you will be using the cooling energy demand of the buildings to reheat the ground, and therefore you don't need as big a number of boreholes. And what this actually resulted in is, when this optimization was complete, was to reduce by 50% the number of geothermal boreholes that should be drilled to supply this village, compared to if each building had decided to drill its own, which anyway was not very feasible. But thanks to this, not only we could have something which could potentially work, but even have a reduction in the investment needed. And on top of that, to supply cooling needs, which we could demonstrate were growing. And this is really important because traditionally in this part of the world, active cooling is not used. We don't have air conditioning in general. And so there is actually even some pushback when we suggest that it might be needed in the future. So in this case, thanks to the energy demand demonstrations, we could show how this demand is going to change, how it's going to increase. And actually this could create a real problem in the future if you don't plan for it now. And so I think that actually that's a really important service to be able to provide, to be able to understand how this new cooling service can be provided, and actually can be provided also sustainably. So in the next part, I'd like to show a bit more our software. So I will exit the presentation and switch over. And I want to present, so this is our tool, Tessa, and I will present a case study we have ongoing in the village of Corsier, so here in Geneva, and explain to you a little bit the process that allows you to go from pretty much an outline of an area of interest to a 5th generation system with geothermal boreholes optimized to supply energy. So here what you see is the initial state. So the base case, we have the village. We've already selected an area. I won't go today into details of the actual workflow, but if you're interested, we are very happy to give you an introduction and onboarding. We're able to select a perimeter, get all of the information about all of the buildings here, and get straight away, thanks to our energy demand and heat models, the current state. So we see actually this is using mainly fossil fuels today, and that's why we have a very high CO2 emissions. I mean, CO2 intensity of 300 grams per kilowatt hour, to give a bit of a benchmark, means that this is almost entirely fueled by fuel oil, so mazout. So a polluting area. What we see in this case study is that we have some green space around, and these could be an interesting place to put geothermal borehole fields. And thanks to our software, this is actually, as a baseline, already very simple. If I switch to the next case, we can see that I have already prepared this geothermal borehole field, here represented by the actual boreholes in the ground. So we have a tool, we have a toolbox. Again, I'm not going to go into the really full tutorial, but to give an idea of what's possible. With our tool, you can create very quickly a layout of boreholes in a given area, dimension these, calculate the spacing, and behind we actually run a simulation of the boreholes and how they interact with the ground. So this isn't just a geographic representation. It's really a simulation of the borehole fields. To run this simulation, we've created one, and then you have all the different parameters you can put in. And so in this first case, we're actually doing what we call a 3G or arguably fourth generation system, in that we are actually supplying a network at high temperatures, but using geothermal, shallow geothermal, which has low temperatures. So concretely, that means we are having a network which would run at around 80 degrees from a borehole field, which is extracting heat at generally under 20 degrees. And for that, we need to add a heat pump to increase the temperatures and circulate in the network. So this is not the most efficient way to use this, but this is the first base case. In this case, what we actually see is that when we run our optimization, I can go here, we see a rather peculiar looking supply curve. What is the supply curve telling us? It's actually telling us that we're limited by the size of the borehole field. Because this system is not efficient, we're not able to actually supply all of the energy we need in order to address the needs of this village. And this is one of the reasons we see this evolution of district heat generations, because to use low temperature renewable sources like geothermal, you need to change a bit the architecture of your systems. You need to change how you're going to do them. And also you see some opportunity, because in this case, my buildings tab, and I look at my energy demand profile, I'm only providing heating. So what I'm actually doing is building a system that's going to last a long time, but which is actually not really very future-proof, because it's not providing cooling needs, which we know from other work actually in this area are going to increase very much in the future. That said, we have managed to reduce CO2 emissions from the buildings themselves to zero. So we have a significant reduction in CO2. We can already talk finance. So our approach with the software is most of what you see actually can be largely auto-generated by simply selecting the area, saying, in this area, I want to create a borehole field. In this area, I will create a network. Software takes care of most of that. You can, of course, then come in and edit to refine the case. But what's really nice is that you can do this, and then straight away, if I can swap over to my finances tab, for Switzerland, we have already default data. In one click, you have all of the cost projections. So we already have a pretty good idea of the cost of building this network in this place, so levelized cost of energy, the upfront investment that you would need, a bit how this is the breakdown of this investment. So you can see, of course, being a heat pump driven system, we have very high investment costs for heat sources, for example, and how the revenue will look instead. So in this case, we've got a 14-year payback period, quite long, but on a project that should be, an infrastructure project that's going to exist for maybe 30 years, 40 years, not so bad. Now we're going to swap over to the fifth generation case. So if I switch back to the design, in this case, what we see is we've planned for the future cooling demand, and we've seen that it's actually started to increase. And thanks to this cooling demand, we can actually densify the geothermal field. So it's maybe not immediately obvious to see like this, but what you actually have is that these boreholes can now be closer together, because we're re-injecting excess energy from cooling down the buildings. We're taking that energy out of the buildings, and we're sending that back into the boreholes in summer, and that's warming up the earth slightly so that we can recover that heat in the winter. And thanks to this, we can have more dense boreholes. We can increase the specific heat extraction rate, and we can get closer to our energy demands. We can see this is going to be significantly more expensive. Actually, it turns out not that much. And that's what's something that's really nice. And what's also a bit of a balance here is that in this case, to design a 5th generation system, what we need to do is we send low temperature fluid around the network, around the loop. Instead of having a large heat pump, which is trying to deliver these 70, 80 degrees, which is of course very inefficient. But for most buildings, we do also need a booster heat pump, what we call a booster heat pump. So for most buildings, they need to have the temperature of the network increased to be useful inside the house. So that's another cost. That cost we have been, we actually included in the cost of providing energy, but of course, it would be up to the business model of the specific case, whether that would be something that would be paid for by the building owners or the network itself. But what we can immediately see is we can start developing different scenarios, developing different business models, using very clean, very renewable energy source, which on top of that provides now cooling as well, because this of course is the levelized cost of energy for heating, but cooling essentially is what we call free cooling. You get free cooling services as a bonus. Today, actually, we don't have many examples of business models of people selling cooling energy, because you're not actually selling kilowatt hours anymore, you're selling negative kilowatt hours. So that breaks some brains in the process. And of course, as an output, we can also see what that looks like in terms of the overall energy balance. If we want to dive into a bit more detail, we can see really Sankey diagrams of energy coming in from borehole fields, entering the thermal network, entering booster heat pumps to increase temperatures. So we have actually the ability to then drill down into a lot of detail and really get deep into the design, and of course, perhaps go back, change things if necessary. And if I switch back to my presentation, I can just give an idea of the comparison then between the 3rd and the 4th generation. So this is the 3rd generation, relatively straightforward in the sense that you have electricity coming here in the Sankey diagram, powering a heat pump. So some of it powering directly the heat pump, some of it entering the borehole field to drive that, and then entering the thermal network with a certain amount of heat loss. With the 5th generation systems, it is a lot more complicated, but you see some neat things. Firstly, I want to draw attention to this little fellow here. This is the thermal synergy. Since we're doing heating and cooling, it's possible occasionally that there's actually heating and cooling demands at the same time. So when you have crossover, or when you have a mix of activities, for example, if you have a commercial building that might be air conditioned, might be using more cooling, you can actually have cases where firstly heating and cooling are happening at the same time and they can be balanced out. And then you also have the fact that you have a seasonal synergy, because some of the energy that you essentially inject during summer is going to be then recovered in winter. Then the rest is classic. You have electricity powering heat pumps for the network, driving borehole fields, and also running thermal network for the cooling. A few feature highlights that'll maybe answer the questions you didn't know you had. So the first is to go a little bit into more detail of this design and dimensioning of the borehole heat exchange. So as I mentioned, we can really simulate what's happening in the ground. So what we can do is we can do preliminary sizing just based on a borehole depth and a target thermal power. Now, this is quite common. You can use reference heat exchange rates, so watt per meter. This is, which can be generally 30 to 40 as a default value. It's something you'll find in construction standards. So this you can do very quickly. You give it an area that you want to generate in, and it'll do the actual borehole fields. But in practice, if you're actually going to build something like this, you really do need to optimize the borehole field to match the energy demand. And traditionally, what people would tend to do would be have one tool or maybe a spreadsheet in which you give a first rough idea of how big your field is going to be using these kind of standard rates. And then you would use another tool, so a separate geothermal modeler, like EWS, EED, software like this, that you would try to prepare your project in that tool and then try to validate it and then maybe bring it back and contrast it with what your network design was. What we actually do is integrate all of those algorithms directly into the tool, so you can directly validate and optimize your borehole field design for the network that you're building, and you don't have to go to a separate tool. And inside it is really what's called a 2.5D simulation. So we actually simulate the diffusion of energy in the ground over time, over many years, in fact, to validate the dimensioning of a borehole field. And indeed, we can not only validate, but really optimize. So you can say, this is my supply curve, this is my demands, this is the area in which I'm able to create borehole fields. How deep should they be, or how tightly packed should they be? And then you can compare and then see how you can really optimize their approach. So in this case, this is actually taking back what we anyway saw, where we had this, in that particular case, 84 boreholes spread 15 meters apart, and a specific heat extraction rate, which was actually relatively low, so only 18 watts per meter compared to the 30. And then you see the total investment cost. So yes, here actually we had 18 watt per meter. So in this particular case, there's not quite enough space for all the boreholes that we'd like to see. So we'd probably have to find a bit more space to expand. I mentioned already some of the other features important, that we can dimension pipes. So this, again, we're trying to solve some of the pain points in developing these systems. Again, what we tend to see when we did work before is people would have an overall view of the system, so do a rough calculation based on the number of buildings, how much pipe you're going to need, and then when you have to actually size those pipes, you have to move to another tool to do some hydraulics, calculate the dimensioning, and so on. And again, all of this now, we integrated that directly into the software, so you can dimension the pipes, you can dimension the boreholes, you can dimension other heat sources, all inside one tool. And if you want, you can come back and modify. So let's say, for example, you already have some pipes which are built, you can actually set those by hand if you know they're already there, or if you want to anticipate capacity increases and so on. That's just some detail. Again, with this idea of looking to the future, we also anticipate that maybe you start with a network which connects only some number of buildings, and then in the future will connect more. So of course you can grow over time by using multi-stage scenarios. So again, this is something I'm not going to go into detail of how you can do it, but if you want, we can of course schedule a demo. One more final point, perhaps. Since we were talking a lot about future energy demand, as I was mentioning, with the cooling demand that increases is a key point. But actually, also the renovation of buildings is something that. So with our building energy model, we can of course also anticipate how building energy demands are going to change, and this causes some interesting effects, which we like to highlight also when we're asked to give our expertise, but we can also let you discover in your own cases, which is, for example, that often the buildings which are today the oldest, most high-consuming buildings, which are often the first to be targeted to be connected to a network, are also the ones most likely to be renovated. And when they're renovated, they might become actually the most efficient buildings in your entire district. And so this, of course, has a big impact on the power, the sizing of pipes, how your dimensioning, your cost, and your energy sales profile. And so with that, I'm going to wrap up. I've already shown you the CapEx, OpEx calculations with our nice financial report. Many details we can go into there. And of course, yes, to mention that we've shown these nice little villages, very lovely places, but of course, many places are not so tiny, and of course our software is perfectly scalable to much larger cases that should you